So my name is Jessica Lundquist. I'm a professor at the University of Washington. And I'm going to start pretty high level with how can we link measurements and modeling across disciplines to improve both seasonal snow and glacier research. I have a picture of a salmon jumping up a stream in the Solduck River because to me in the Pacific Northwest, that's where the snow and glaciers come together to determine whether we have enough water for the salmon to make it upstream. And let's see, many things. Let's see how I can advance my slides. All right, so starting with, we're talking about snow and ice as interdisciplinary research, but I wanted to start with emphasizing that we need to think of this as the entire hydrologic cycle. In particular, we really need to understand both precipitation, how much snowfall is falling out of the sky, and runoff as two measurements and communities that we also need to bring in to really understand seasonal snow, glaciers, and ice. And I've got a picture here of runoff from the Merced River in California, which is snowmelt dominated, and just how much both the timing and the amount vary in different years. So when you think about measuring and modeling the snowpack, I think about three phases. There's, and what you're seeing here is a graph of snow depth and month of year, where the colors show the evolution of snow density, where green is higher density. And then underneath is just my graphic approximation of stream flow and how that relates to snow depth. And that doesn't work. Sorry, that one will work. So the first phase is, I'm going to argue the most important, is how much snow accumulates. This is actually what we know the least about. It depends on precipitation, wind, and snow drifting. This initial phase, just how much snow we get on the ground each year, is going to determine our total volume of runoff from snow. It's also going to be extremely important in the snowmelt and disappearance at the end of the season. To demonstrate just how important this is, I just want to show a little bit of work from Mark Rowley, who asked the question of what data matters the most to model the snow. This came out in two papers in 2015 and 2016. And he looked at 4 different locations with very good snow and atmospheric measurements across the Northern Hemisphere, in Naviet Creek up in Alaska, Reynolds Mountain East in Idaho, Senator Beck in the high mountains of Colorado, and Col de Port in France. And he started with, if you actually measured precipitation, how well could you model snow? And then he perturbed everything else that might have something to do, incoming energy balance and model parameters. And what I want you to take home from this is that actually, if you have precipitation, you actually can do a pretty good job modeling how much snow we have. So at the warmer sites, and here I've circled the France maritime site as well the Idaho prairie site, that where we measured precipitation, the gray lines indicate the entire ensemble. The red line indicates how the model worked if we used every locally measured observation we could get our hands on. And then the blue line actually just used temperature measurements to estimate all the rest of the atmospheric variables. And in these two sites, measured precipitation, we weren't that far off. The other thing to notice is that places with colder, lighter snow, such as the Alaska tundra or the Colorado alpine, probably places more likely to have glaciers, with the exception of Pacific Northwest glaciers, that actually our measurements of precipitation were not accurate enough to model the snow. Blowing snow, wind drifting, and undercatch in the precip gauge. You see the black line in Alaska are the observations, and the observations of snow on the ground did not match the observations of precipitation falling out of the sky. At most sites, if we have accumulation right, we can melt. But I also want you to note that the next thing that matters is the midwinter energy balance. This is an evolution of the temperature of the snowpack, and it's going to determine, the onset of snowmelt and the onset of stream flow. If you return, and I just wanted a quick graphic to say that most snow models we're using are based in well-known physics, and they perform well given accurate meteorological forcing data. That said, everywhere we work, we have a hard time coming up with a good estimate of that data. If you look again at these model simulations, all the different gray lines, you'll see that where the models diverge is actually this critical point where all the red arrows are pointing is when melt turns on. So the next thing we want to know after we know how much snow is on the ground is when the melt turns on. This can be tracked with the snow surface temperature, which we can observe in situ or remotely. And here's just a graphic showing the evolution of snow temperature, both at the surface, the top of the snowpack, and throughout the entire snowpack, where blue is colder and orange is warmer, representing the energy balance. The last part is the melt season. And this determines our snow melt and when our snow disappears. And this timing of snow disappearance is going to determine the onset of glacier melt, the onset of sea ice melt, and the late season summer low flows, which I'm showing you here, this my salmon again, is that even though volume-wise, this is much smaller than the total amount of water from the snow accumulation, this is very critical to our ecosystems. And this depends not only on the energy balance, but also on how much snow accumulated and how it was distributed, which Dan is going to talk about a little bit more in his talk. Given the 10-minute limit, I'm going to jump from the science to a little bit logistics to bring up for discussion. I wanted everyone just to be aware of various snow working groups. In February last year, the first NASA SNOEX field campaign took place in Grand Mesa, Colorado, which was studying snow and forests and remote sensing techniques, many of which are nearly identical across the snow and ice communities. We are currently planning the second SNOEX field campaign, and we're determining both the field site and the focus questions for winter 2019-2020. It's a very open discussion at this point, and input is welcome. In terms of outreach for these kinds of activities, NASA maintains the snow.nasa.gov, which has all the SNOEX information and the official NASA information. I maintain what's called the ISWAGR website, which is International Snow Working Group for Remote Sensing, bad acronym, but here's the link. We also just recently posted on there a interactive website about the economic value of snow in the Western US, talking about how much water comes from snow and what that is worth in dollar amounts. We've also been working hard on educational outreach. We hosted a snow field school in January this year in Colorado with 30 students, many from glacier backgrounds as well as snow backgrounds, working on one in 2019 to be held in Montana. Matthew Sturm is taking the lead on that. I also just got back from the International Snow School, which took place in February in France. And work is underway by Martin Schneebly for 2019 school that is planned to be near or on the sea ice off of Norway. And I've got a link to his website from the France school. Finally, I just like to throw out there that there are organizational impediments right now for snow and ice to work together. The University of Washington, they recently had a Future of Ice initiative and told me as a snow person I wasn't supposed to be in it because the future of ice is not snow. Future of snow might be ice, but that's a different story. As a result, snow on glaciers or ice, which are very disciplinary similar, is often ignored, and I think it would be helpful to get some Dear Colleague letters encouraging interdisciplinary collaboration. And also just in terms of our outreach and our snow schools and glacier schools, we could trade instructors more to better. Someone want to comment? I'm done. So just in summary, science-wise, and this is actually a picture of Matthew Sturm and I taking measurements of snow on sea ice. So we do that sometimes. Snowfall precipitation dominates uncertainty in seasonal snow and likely glacier evolution. The biggest term is how much falls out of the sky in the first place. The energy balance dominates the onset of melt and melt rates. And actually our models are getting much better at this, and our abilities to add remote sensing to improve this are rapidly increasing. And with that, I will return my screen to everyone else so we can stay on schedule and allow plenty of time for questions. Thank you.
All right, great. My name is Dan McGrath, and thank you, Jessica, for that great introduction. Today, I'd like to give a quick talk on how much snow is out there, considering spatial temporal snow accumulation patterns on glaciers. I'd like to acknowledge the support of co-authors here, Louis Sash, Chad O'Neill, Chris McNeil, and Emily Baker, who have all contributed an awful lot to this work here, along with funding support from the U.S. Geological Survey. So at the expense of being somewhat redundant here, I want to provide a little bit of a justification for why we really care about the distribution of snow on glaciers. This mass input to the glacier represents 1/2 of the mass balance equation. And so if we're going to accurately monitor and measure the mass balance of glaciers, we need to know how much snow is being added to them. Second, this seasonal snow really helps determine the albedo of the glacier surface through the melt season. And so that very strongly influences the melt rate and the transition to melting of glacier ice, as Jessica suggested. So furthermore, we need to know this distribution of snow if we're going to be able to implement sophisticated glacier mass balance modeling. There's more than 200,000 glaciers in the world, and we're obviously not going to measure all of them, but we need some way to meaningfully distribute snow on these glaciers to accurately implement these models. All of this really comes back to the meltwater that's produced by these glaciers, both in terms of the seasonal mass turnover of the seasonal snow, and then in a negative mass balance year, the addition of water from melting of glacial ice. These systems are changing in a very significant way. There's some recent work by Jordan Beamer and Dave Hill looking at the hydrographs or stack plots looking at the monthly volume of water into the Gulf of Alaska. And you can see on the left there, that's in the modern, this kind of single distribution. And then in the future, this bimodal distribution where we have a lot less precipitation falling as snow. And so rather than accumulating snow in that October-November timeline, it's falling as rain and immediately running off. And this is for an RCP 8.5 climate forcing. And in this fabulous figure from Chris and Tim, published in O'Neill et al. 2015, it really illustrates just how tightly coupled glaciers are to the downstream ecosystems, whether it's the biomes on them, the fish habitat immediately downstream, to the nearshore oceanography, the ocean currents, carbon uptake. Really, this water that's sourced from seasonal snow on these glaciers really ties these whole systems together. So I just want to provide a kind of high-level overview of a variety of different approaches that are currently utilized to measure seasonal snow on glaciers. Historically, and I'd say still used very extensively, are point observations. N equals 1 to maybe 10, or if you're really lucky, up to 30 point observations, whether those are from pits or probes or glacier mass balance stakes. Occasionally, some glaciers that are being monitored will have a nearby precipitation gauge or a sonic sensor. And I'll talk about those a little bit more. In the last couple of decades, there's been an increase in the number of distributed observations. This really increases our sample size very significantly, but that doesn't come without additional issues in the implementation of these techniques. So I'll touch on these different techniques talked about there, listed there. And then lastly, some variety of different modeling approaches, whether these are downscaling of regional climate models, or using terrain parameters to extrapolate point observations of snow water equivalent out, and then occasionally the implementation of a physically based model, but very much dependent on available meteorological data. And as this figure suggests down here, we want to be able to go from these actual point observations to much larger glacier areas. So 2 square kilometers, 10 square kilometers, 100 square kilometers. Can we use these point observations to get a meaningful estimate of how much snow is out there so that we can answer all those questions that I posed on the first page? So in terms of point observations, it's one universal thing between all of our communities is our ability to dig snow pits. Sometimes the glacier community is stuck digging very deep snow pits. This is a photo from Bob Krimmel on South Cascade Glacier in 1983. That technique is still widely used. This is a map of Wolverine Glacier, one of the USGS benchmark glaciers in Alaska. And you can see in those red circles a series of stakes. Those are stakes that are part of the long-term mass balance record. And so we measure seasonal addition or loss of mass from those, integrate that over the glacier area to get an estimate of the glacier-wide mass balance. Occasionally, smaller glacier mass balance programs will have a higher density of observations. This is some work here by Nicholas Cullen on Brewster Glacier in New Zealand. I think this glacier is around 2 square kilometers, and you can see the higher density of observations, but this is not feasible to be maintained on glaciers much larger than that. And then lastly, as I suggested, some glacier monitoring sites will have some sort of precipitation gauge. These precipitation gauges are obviously well suited for measuring liquid precipitation, but not so much frozen precipitation, particularly in a windy environment. And so this figure in the bottom here from Rasmussen et al. Illustrates just the catch efficiency decrease as we see increasing wind speeds. And really, once you get above a few meters per second, you're getting very low catch efficiencies. So some of these distributed approaches, the first one is ground penetrating radar. And so these radar systems are mounted either behind snow machines, skiers, or beneath helicopters and are carried or traveled across the glacier surface. We measure the two-way travel time to reflectors of interest, and that's what's being illustrated down here. You can see this red line where I've identified the seasonal layer. This is a little bit more complicated in some ways in the glacier world because we have firn. So all these layers down below here are previous year's snowfall. That's adding up to add to the mass of the glacier. So identifying this layer can be quite challenging and requires a lot of in situ validation. But nonetheless, this gives us a great way of estimating snow water equivalent across the glacier once we have convert that travel time to a depth and subsequently a SWE with some calculations / assumptions. And some very relevant references down there at the bottom of where this has been implemented in other locations in the world. The second distributed approach that's really quite applicable here are volume-based approaches. So in the top here is an example of LiDAR collected in Switzerland, published in SNOTEL Data 2013. On the left, you see this raw LiDAR field over the glacier, and it's a pretty peculiar pattern. We have the highest accumulation down in the lower part of the glacier, the lowest accumulation up here in the upper part. And really what's going on here is that glaciers, because they're flowing, have an emergence velocity. So once you model that emergence velocity, which is shown here in this middle panel, which can be on the order of a few meters per year, and subsequently correct your LiDAR data, you get a reasonable distribution of little snow down and upwards of a few meters of snow up high. I have this arrow leading to this tree here because I think this is an interesting connection between the glacier community and the seasonal snow community, that the emergence velocity and vegetation represent kind of the thorn in the application of this method. They really challenge the widespread use of this because for us, modeling the emergence velocity requires additional data and produces additional uncertainty in these observations. On the bottom here is some work that David Sheen's doing, where he's using stereo image pairs derived from the Worldview constellation to measure snow depth on Mount Rainier over 3 years. So spaceborne, can be widely implemented over a large area and quite precise or quite accurate in its estimate of elevation change over that period. But again, this is dependent on the emergence velocity, which these have not yet been corrected for, but a very promising result, showing the distribution of snow on Rainier. Just quickly on touching on these different modeling approaches, as I suggested, statistical downscaling is often implemented in the glacier world, where we take a regional climate model and downscale that to your site of interest. As is often the case in the seasonal snow, these are in complex topography at high elevation, and downscaling to a pixel resolution of a square kilometer is just not good enough. Like the scales that we need are much finer than that. And so that's a problem with this approach for looking at the actual distribution of snow on these glaciers. The second here is a terrain parameter-based approach. This is widely implemented in the seasonal snow community, but where we take point observations, we relate those point observations to a range of terrain parameters such as elevation and curvature, aspect, different parameters describing wind redistribution such as Adam Winstrol's SX and SB. And then we can extrapolate once we establish these coefficients over the entire glacier area. And that's what's shown here for Scott Glacier outside of Cordova, Alaska. And then lastly, although it has not seen widespread implementation, due to the lack of meteorological forcing data in these locations. Some physically based models, in this case, an atmospheric physical model, looking at the wind field, the surface normal wind velocities proximal to the glacier, which is outlined there in black in Switzerland. This is very much dependent on where we're going to get this preferential accumulation on the glacier, where the snow is being moved around to. So I just want to highlight a couple of pieces of work that we're doing out of USGS and the Alaska Science Center. First was some work we published in 2015 looking at kind of a regional snapshot of SWE throughout Alaska. So 7 different glaciers from the coastal environment with Scott and Wolverine to the interior continental climate with Eureka and Colcana there. And you can see on the top panel, SWE as a function of a normalized elevation, and then these SWE gradients really illustrating this regional control, distance from the coast, distance from your precipitation source as control on this SWE gradient. In 2015, we collected this high resolution or high spatial data set. These are 250-meter grid over Wolverine Glacier. So this provides, rather than n equals 3 in terms of our point observations, we're up to n equals almost 500,000 points of SWE on the glacier. And so this gives us a really good way to test what the actual solution is in terms of, what winter balance is, what we call BW. And how much of this data is necessary to reach that. If we start taking off some of these lines or a lot of these lines, how much uncertainty do we add to our BW solution? This also allows us to better assess our uncertainty in both our BW solution today, but also allows us to look back in time and say, okay, we have a series of states that have been maintained for 50 years. What kind of uncertainty do we have in those states, and what are they actually measuring in any given year? And I'll talk a little bit more about the spatial temporal variation on the next slide now. So we take our GPR point observations, this is shown for 2013, and then we're exploring a variety of different ways of extrapolating these out over the glacier area, whether this is a simple elevation gradient, or a terrain parameter multivariable stepwise linear regression, or a terrain parameter decision tree. Either way, we get some sort of distributed field. In this case, I'm showing the multivariable regression results. We can then integrate that over the glacier area and get an estimate of the winter balance, which is shown there in the bottom right quadrant of that figure. And we also start to think about how stable these accumulation patterns are through time. So 2 different approaches here, the normalized range. So basically we just take the glacier, for each pixel, we take the SWE in that year, we divide it by the mean for the entire glacier, and then we calculate the percent difference from that normalized value. And then we look at the range in those percent differences over the entire interval that we have these observations. So the less range you have, the less variability you have. That pixel is always measuring or always having the same amount of SWE from year to year, at least scaled by the magnitude of the SWE. And a similar approach here with the R squared that I won't go into in the name of time. But what we're finding is that a good percentage of the glacier, upwards of 80% of the glacier, experiences relatively low variability, less than 30% variability. A small percentage of the glacier, about 10 to 15% of the glacier, experiences a significant amount of variability. Obviously, these are spots where avalanches might come down or wind drifts are not persistent from year or consistent from year to year. The other thing that these winter balance estimates from the glacier, from the GPR allow us to do is compare it to the glaciological stake estimates, and that's what's shown here in the bottom left. So glaciological on the x-axis, or GPR derived on the y-axis. You see we're doing pretty well at Colcana, pretty good agreement between these 2 different approaches. And then at Wolverine, the GPR solutions are suggesting that we're seeing a greater winter balance than the stakes are suggesting. So there's spots on the glacier that are getting more accumulation than we're able to resolve with just a small stake network. But still really quite impressive that just a limited number of stakes, in this case 3, are actually doing a pretty good job of estimating the glacier-wide average. But as I suggested on those earlier slides, we really do need to know what that spatial distribution looks like on the glacier if we're going to have being able to meaningfully implement these distributed mass balance models. And so I just want to leave us with these 3 questions that we can come back to at the end. What can these communities learn from each other, and how we're measuring snow and the importance of snow, and then also what opportunities are there for collaboration between these communities. Thanks.
Great, thanks, Dan. So we're going to switch to Adrian next, who's actually sitting right with Dan.
We're getting there. Bear with us. Okay, share screen.
Great. Hey everyone, my name is Adrian Harpold. I'm an assistant professor at the University of Nevada in Reno. And I am showing one of the few glaciers in Nevada. This is below Wheeler Peak and Great Basin National Park. And relevant to the story I'm about to tell, there's actually a SNOTEL observation within sort of half a mile or so of here. So Dan and Jessica have really done a brilliant job of setting up kind of our infrastructure for making seasonal snow measurements. And I'm going to really focus on a couple of little science vignettes that I think highlight some of the challenges that we face and maybe some of the simplifications that we're making. So think about humidity, both from snow accumulation as well as ablation. And then I'm going to talk a little bit about snow drought. So this first example is about trying to get accumulation correct. As Jessica mentioned, without being able to get precipitation in the phase of precipitation correct, it's very challenging to estimate seasonal snow cover. So how do we do this? A lot of times we use air temperature. And air temperature is a large control on the energy budget of a falling hydrometeor, but we also know it's not the only control. And so when we look at common empirical ways of making these measurements like this dye relationship, we see that there's a lot of snow falling above 0 degrees Celsius, right, above freezing. And that there's a number of factors influencing that, but a large part of that has to do with latent heat loss as the hydrometeor falls. So there's corrections you can make to bring in more mechanistic understanding to this. And one is to use a relative humidity correction. And so we take this relationship developed by Ficio Brino that matches several other relationships that have been developed at different sites to correct the temperature at which snow changes to rain based on relative humidity. And what you see is that at lower relative humidity, you can have snowfall at warmer temperatures. So does it matter? Well, we can take those models, this dye model that is only temperature based and the TRH model that also includes humidity in addition to temperature, and we can play these out over the future using our GCM projections and see whether they produce different predictions. And so the individual points here are basins in the Western United States, and falling above in the positive means that the temperature-based method is predicting a greater amount of rainfall, or the humidity is predicting a greater amount of snowfall. So you see the general tendency is for this humidity to buffer changes from snow to rain. And so if we're not including that, we're going to have potentially some biases, and those biases are very much not random. They're driven by humidity distributions. So that's kind of the vignette one about snow accumulation. And I'm going to talk about two other pieces that both really rely on the SNOTEL network. And my guess is most people on this call are very much familiar with the snow telemetry network, which is run by the Natural Resource Conservation Service. It sets mostly on old snow course locations that go back to the 30s, 40s, 50s. But these SNOTEL sites went in the early 1980s. And when they went in, well, and since then, but the earliest one were the 1980s, 1979 or so. So they initially were just the SWE and precip sensors. They've since come back and instrumented all of them with temperature, although there's been issues when they switched some of the temperature gauges, and they've also come back and put in snow depth. However, what we really don't have is much else about the climatological forcings at these sites. So that leaves us with a challenge, right? If we want to go back and look at the SWE and precipitation at these sites, we are going to have to make assumptions about forcing. But fortunately, we're good at making assumptions, and there's lots of forcing data sets available for us to choose. So what we've been doing is harvesting the forcing data out of different gridded data products and overlaying that on the SNOTEL. So you can see that this is going to be a challenge to get the energy budget, to do energy budget modeling like Jessica alluded to, but we can start to look at patterns of response. And what I want to show you is sort of the richness of what a SNOTEL pillow lets you do. So now we have continuous 1 hour data. I'm showing daily data, but the data is collected 1 hourly. So we can start to analyze this Niveo graph, the SWE graph, in different ways. And the classic way is to look sort of at the spring ablation season. The melt season, I think, is as Jessica referred to it. But at this particular site, we're also looking at these mid-winter ablation events. And we're using the fact that we have a daily response to accumulate and keep track of how much ablation we're seeing sort of prior to peak accumulation for that year. And then we trend line through this. And what's so amazing now about the SNOTEL data set is we have 35 years of data from over 450 stations across a dramatic climate variation. And what we see here is the statistically significant trends are really all towards increased winter ablation. And that really has a bullseye over the Pacific Northwest, and very much not seeing that increased winter ablation in the Southern Rockies and farther southwest. And why is that? Well, we can plot that out against that winter ablation rate against mean winter temperature, and we can see that while there is generally more winter ablation at higher temperatures, that in fact the sites with higher humidity in the winter really show a dramatic increase in the winter ablation. And there's a cutoff around 3.5 grams per cubic meter of absolute humidity where we really see a pickup in the amount of winter ablation for the same temperature. And this is sort of another way to show that on the left panel here is if you take all the site years and you group them by humidity, so going from cold colors to warm colors is going from low humidity to high humidity. As a function of temperature, you really see much higher winter ablation in more humid places for the same temperature. So that means, one, that you'll see more winter ablation for the same temperature, but two, that potentially they're more sensitive to increasing winter ablation from increasing temperature. And those regional patterns play out in the bottom right, where the Pacific Northwest, the red dots, as you warm that system, it becomes more humid and you cross this empirical threshold at a relatively low temperature. In the Southwest, where there's just less water available, you have to import a lot of your water vapor, you can warm that system and the humidity doesn't increase as dramatically. In fact, it never, according to this moving average, crosses that threshold. All right, and I'm going to make a pivot and do one last little vignette here about extreme lack of snow accumulation. And so this 2015 year was just a really incredibly bad snow year, kind of reminiscent in some ways of this year along the West Coast. And what we noticed when we started to look at it was that there was really two drivers of low snowpack. So the dots on this map are the snow courses. The dark red are essentially extreme low snowpack against the historic average. So extreme low snowpack everywhere, but if you look at the background color, the lighter whites and greens are near average precip. So up in Oregon, we were getting close to average precip, but well below average snowpacks, and down in the Sierra Nevadas, we just simply weren't getting precipitation. And so we've taken an approach where we have sort of classified dry snow droughts as a lack of precipitation versus two types of warm snow droughts, one where the precip is falling as rain and not accumulating, another where it maybe is falling as snow but is ablating or melting and therefore not there at the times when we want it. So I won't get into the details, but you can start to map this across the Western SNOTEL sites through some assumptions and just sort of typecasting this. And what you see is that warm snow droughts are really important. So absolutely, if you don't get precip, you're going to be in a snow drought, but the effects of energy, both on phase and ablation of snowpacks, are really important kind of everywhere, but particularly in the maritime. And the right panel is showing the breakout of warm rain and warm melt. And again, you see very distinct regional patterns suggesting that there's different sensitivities in these different regions. And that's what the last slide I have here is sort of, I guess there's two more. There, these different regions, these are ecoregions in the West. You can really think of these as mountain ranges, and how frequent snow drought happens as a function of elevation. And while you see elevation effects, and sometimes those slopes are actually relatively consistent, there's really no master elevation control on snow drought in the West, which I think reflects, again, the sort of mountain region scale variation in hydroclimate, and therefore different sensitivities to snow drought. And this is the last slide, and this is sort of playing up those regional sensitivities. So if you do a multiple linear regression on these really poor snowpack years, so below average snowpack years with precipitation, the degree days, which is a metric for temperature metric for the amount of energy available, and the wet day temperature, or the temperature on days of precipitation, you see regional differences where the Southern Rockies are kind of one in member where they're very precipitation sensitive, where the Southern Cascades or the Oregon Cascades are another in member where they're much less precipitation sensitive, but very wet day temperature sensitive. So again, the hydroclimate, the variability of all these different climatic and topographic controls really gives rise to different sensitivity. So a couple closing thoughts. I'm on the humidity bandwagon right now, but just as a, as a way to kind of move past temperature as the only control on our future trajectories of snow, I think it's worth starting to think about humidity both for accumulation and ablation processes. And I did not see Jessica's slides, but I think I kind of knew that she would talk about this as well, which is, I'm taking gridded data sets to really supplement the SNOTEL data, and we're learning things that way. But if we really want to get at the sensitivity in a very mechanistic, process-based way, we need better energy budget, both the incoming energy budget of the forcing data, the climate data, as well as the energy budget of the snowpack itself, some of the stuff Jessica was showing with the temperature of the snow and all of that. So thank you very much for letting me speak.
Great, thank you, Adrian. Is Laura on the call?
Hey Shad, this is Joe. Laura just called me. She unfortunately she had a calendar snafu and she's not going to be able to make it.
Okay, that's not a big deal since we're 40 minutes in. So let's try and enter into discussion mode. We've had 3 excellent talks on snow from both a seasonal and a glacier viewpoint. Does anyone want to ask questions to any of the speakers? Please don't be shy.
As long as we got a dead mic for a second, this is Peter Griffith from NASA Arctic Boreal Vulnerability Experiment, and I just thought I would toss out for the SNOX folks that our next airborne campaign is likely to be in 2020 and include some winter or shoulder season at least flights. And I've talked with Ed Kim and Ann Nolan and some other folks from SNOX, but certainly encourage collaboration on the next SNOX campaign with us.
Hey, Peter, if you can post that on the website, that would be real helpful. Thanks.
So if no one is going to jump in, I'll ask a question and any of the speakers can address it. But it seems unrealistic that we're going to get incoming or outgoing energy measurements distributed across the landscape anytime in the near future. So, but everybody's calling for that as the most important thing to move forward. So what do we do?
So this is Jessica. Can you hear me?
Yep.
Yep, excellent. So I think we've got 2 things that are working right now. One, our ability to remotely sense snow falling out of the sky is still incredibly challenging. Many people at GPM are working at this, but they don't have it yet. And so I think the best step is that we actually need to measure snow on the ground after it falls out of the sky. Then we can retrospectively correct our precip models for what's coming. I think that altimetry methods are incredibly promising. Dan showed a lot with LiDAR. There's challenge that the glaciers move underneath the LiDAR. So your baseline is changing, but I think we can still, with more of these measurements, make a lot of progress there for getting our precipitation right everywhere by correcting it with after the fact measuring what we see on the ground. The second thing in terms of the energy balance, I went through really quickly, but we can remotely sense the surface temperature of the snow and the ice right now, and we can actually use that to constrain a lot of the uncertainty. The other thing the modeling results showed was that even when we don't have the measurements, or we only have measurements of temperature, that we can actually constrain most of the other melt forcing variables fairly well. If we get accumulation right, we can narrow our errors quite a bit. So I think remote sensing has a lot of possibilities that we can use globally.
And I'd add one more thing, which is these atmospheric models are really developing, and they're starting to run, say, WRF at scales where it is actually more appropriate in complex topography. I think the computational and storage and data transfer limitations are still a problem, but I can see that Keith Musselman was on the call, and they're doing some really, I think it's helping to constrain the forcing. It's not a substitute for observations.
Excuse me, can I jump in and ask a question about climate modeling? So I'm doing research for radio transfer of snow on land ice and on sea ice both. So currently in the CSM, the snow radio transfer on glacier is modeled by SNCR, which is in the land model scheme. Then the SNCR will just pass the flux below snow layers to glacier. So I was wondering if this is something you are thinking about how to revise it, or how to make it better, or how to make it more sophisticated radio transfer modeling for glaciers. Yeah, I don't know if this is the right community to ask a question, but yeah.
I'm not personally, but perhaps someone else on this phone call might have something to add to that.
And this is Jessica again. So I'm guessing with the SNCR model, you're using a forward radiative transfer model within some kind of microwave remote sensing, is that correct?
Yes, I think, oh, so for SNCR model, I'm only talking about the shortwave radio transfer.
So you're only doing the energy balance with your radiative transfer? You're not?
Currently, I'm only working on the energy balance right now. So this is wondering about how to couple the atmosphere model, land model, and the land ice models.
And so, but AMSR is a microwave remote sensing.
Oh, okay.
So, so I'm guessing that you probably are doing a radiative transfer model to get a forward signal that would match AMSR for microwave remote sensing, and then you're doing some kind of updating scheme to then improve the snowpack?
Yes.
And so, when I showed in my slides, I showed the different layers of the snowpack, the different density and temperature structure of the snowpack medium. And so in terms of microwave remote sensing, all of that internal structure of the snowpack heavily influences your microwave signal, so that you not only need to get the bulk properties about how much snow you have right, but you also need to actually get the density structure and the layering correct within your snowpack. So that is one step, like, just considerably harder in your modeling. And if you go back to my point that we don't know how much snow fell out of the sky in the first place, the problem is that, you know, if you don't get the snowfall event correctly, you'll build your layers of the wrong thicknesses, and then you won't get the right forward model for the remote sensing. So it's still, that is still an incredibly just challenging thing to do. There's a lot of people working on it. But I think we, particularly for deeper snowpacks, such as we see on glaciers and very heterogeneous snowpacks, and places where you get ice layers or wet layers, that is very difficult. It's much better on a homogeneous, such as the Canadian prairies.
Okay. Okay. Thank you.
How about the ecology community? I know there's at least a couple ecologists on the phone, and I'm curious from your perspectives, are the physical scientists that have just spoken headed in a direction that's useful for your community? Jeremy, Steve, you guys want to chime in? They must be multitasking.
So I muted a few people when I was getting some noise. So if you're having trouble getting off mute, let me know. Oh, yeah, let me try to unmute because I think Jeremy is trying to unmute. So hold on. And Tim Bartholomew has his hand up. Let me unmute. Try to unmute Jeremy. Sorry. Tim, you should be able to talk.
I'm going to let these other folks field that question, because that question is not for me.
So I think I've unmuted you, Jeremy. Can you try? No?
All right, this is Steve. Can you hear me?
Yeah,
Yep.
we can. Sorry. I think
Okay.
got Jeremy as well. Jeremy should be good to go too, Steve.
Well, I'll let Jeremy go then if he's available. Otherwise, I can chime in.
Can you hear me now?
Yeah, we can. Sorry about that.
Okay, Steve can hear me through the wall, but no one else can hear me. That's great. So yeah, I mean, in answer to Shad's question, I can see that the evolution of this work, you know, in terms of how it limits terrestrial ecosystem processes, the scale at which the community is starting to be able to pursue things in their awareness of the limiting factors, some of which are very similar to limiting factors that the vegetation experiences, although the seasonality is different. Some of the things that we need to know to do a better job of projecting future changes are similar in their physical nature. And so I'm happy to see the progress. I think also in the Alaska snow community, we don't have access in some cases to the same density of observations in the historical record, nor the temporal disaggregation of the future climate projections. And so we have to make do. I know that Shad and Dan are a little bit aware of some of the work that we've been doing with Steph McAfee to move forward and try to make some of the best approximations we can given the limited data that we have. But this has been really educational for me to see and to understand where we might be headed soon on the terrestrial side to try to you know, maybe collaborate on some of the responses that we see in the terrestrial systems as the snow community's capacity increases.
Awesome. Thanks, Jeremy. Steve, do you have anything to add, or are you happy with that answer?
I'd just add, I'd add a couple of things to that. I think Jeremy's exactly right, but in addition, on kind of a broad brush level here, I think we've got a tremendous amount to learn from this broader community in terms of the distributed measurements, both in acquiring those measurements as well as applying them to understanding the system. So I think there's a lot of potential for crossover there. And then I think just this idea of, you know, developing and thinking through the concept of snow drought, I think can be of tremendous use for all of us, just really understanding the implications of that by nature, it links it back to other parts of the system and gives us a platform to explore some of these issues much more. I think that that's a very fruitful avenue for all of us to pursue.
Thank you, Steve. Tim, did you still have a question?
Yeah, I was wondering if, you know, obviously the challenge of getting wind redistribution is really tough. With respect, I was just wondering sort of how close we are to making serious progress on that and actually being able to predict, you know, if we could even measure the amount of precipitation, do we have a chance in the next 5 years of actually getting wind redistribution? And I think Dan showed a slide of looking at a physically based model that would use the surface wind stress. And when you actually try and validate those models, are they successful in reproducing the observed pattern? Or is there another approach that we could take?
I mean, I guess in terms of the data et al. Paper, which that figure came from, I think they were able to reproduce the pattern, but that's, you know, a relatively small glacier with 2 or 3 weather stations kind of surrounding it. So, a density of observations I don't think exists elsewhere. I guess in terms of our GPR observations, we find that these drifting patterns fairly consistent in time, but there's definitely a variable component to it. You know, you think about storm impacting Green Glacier, your wind speed maybe 50 miles per hour, then maybe 100 miles per hour, and your snow density might be different for each one of those. And so the length scales of your drifting can vary throughout the year, and then obviously that is continuously adding on to itself as it's building out the seasonal snowpack. So I think there's a challenge of, it's a really challenging target, I guess, given what we've seen with the
And so this is Jessica. In terms of modeling, I know the Swiss have been coupling higher and higher resolution WRF models. As Adrian mentioned, if you get down to a large eddy simulation type model that actually handles the whole atmospheric boundary layer, you can correctly distribute wind to the correct places. That said, computationally, I think that's still a ways out to do that over wide regions, but for specific places we can. The other thing is that in most places, the wind direction during storms is from a similar direction. And you know what Dan showed with that you were getting repeatable patterns, that you know surveys at very, very high resolution once or twice can actually give us pattern recognition that we could use for, you know, downscaling all future measurements that would probably get us 80% of the way there in the near term.
Yeah, I would second that. I mean, one way that we're thinking about going forward with these observations is building some sort of kind of climatological spatial distribution map for each of these glaciers that then can be scaled by the magnitude of some smaller subset of observations in a subsequent year. So we know these patterns are relatively repeatable, and yeah, we'll probably get 80% there. We're not going to get 100% there with this approach, but we could get a lot better than if we just, you know, just probed a few spots. If we have an idea of what that looks like.
The seasonal snow community has made some pretty good advancements using LiDAR snow on, snow off, because it's sort of the scale of meters where these drifts form at. It's good for validating models.
Also a citation someone put up in the chat box that people might want to take note of.
Awesome. We've got a couple minutes if there's further questions, or this has been a pretty amazing session of knowledge transfer between communities that don't always sit in the same room. So if nobody has any last questions, I think we can wrap it up.